In the cold, dark void, there are stellar neighborhoods with 10 suns. Forget binary stars, forget even systems with 7 stars. What if I told you that out there astronomers have confirmed the existence of systems with 10 stars? These Decuple star systems are astronomical nightmares. Their gravitational chaos should lead to instant collapse, yet they exist in a bewildering, complex dance. We call these stellar monsters D10 systems. They are unimaginably rare, wildly energetic, and defy almost every rule we thought governed physics and space. Over the next 20 minutes, we will explore 25 unbelievable discoveries astronomers have made about these unthinkable constellations. You will learn how these systems manage a gravitational ballet that should be impossible, what kind of planets they might harbor, and why they hold secrets about the universe itself. How can 10 stars form so closely without merging or being flung into the void? Are there dark forces stabilizing these massive stellar families? Prepare yourself for extreme gravity, bizarre physics, and massive cosmic secrets. What does it take to keep 10 suns orbiting without everything tearing itself apart? Gravitational chaos should tear these solar families instantly apart. Yet they endure these systems of 10 suns, defying everything we thought we knew about stellar mechanics. We call them D10 systems, and they are not just rare, they are almost unthinkable. Now we dive into the 25 unbelievable discoveries astronomers are making about how these monstrous 10-star constellations manage their impossible dance. Think about the most stable thing you know, perhaps a bicycle wheel or a grandfather clock. Now toss 10 entire suns into the same proximity, each one fighting to pull the others in different directions. The energy required to simply exist in one of these systems is astronomical, pushing the very boundaries of physics. Our first unbelievable discovery centers on the sheer impossibility of their formation. How can 10 massive stars be born close enough to form a system without immediately collapsing into a single massive star, or alternatively, flinging 9 of their siblings into the cold, empty vacuum of space? It is a cosmic puzzle that suggests the early universe might have had conditions we cannot even begin to replicate in a laboratory. The accepted models of star formation often predict that when too much stellar material gathers in one spot, it simply merges. But the D10 systems instead fracture, forming multiple separate stars that somehow manage to stabilize into complex orbital layers. This challenges the standard stellar nursery theories and forces us to consider that perhaps a dark, unseen factor is involved in cushioning these gravitational giants from utter self-destruction. Discovery number 1 in the roster of 25 strange facts is the impossible architecture of these 10-star families. Astronomers are now observing that D10 systems do not form through the slow, gentle accrual of matter. Instead, they appear to blast into existence in a sudden, violent manner that produces multiple stellar cores simultaneously. Think of it less like a slow gathering and more like a cosmic bomb going off. This is the formation paradox, the idea that the explosive pressures needed to ignite 10 stars so close together should also scatter them instantly. Yet the stars stay bound. What astronomers are finding is that these systems organize themselves into tight, mathematically precise subgroups. Instead of 10 stars orbiting one central point, they cluster into sets of 3, 3, and 4 or 5 tiny binary pairs, all revolving around a common, distant center of gravity. This is not random clustering, it is structured chaos. This internal grouping manages the gravitational forces far better than 10 individual stars trying to orbit freely. It is essentially a gravitational hierarchy where the small, tight groups manage their internal conflicts so the larger system can remain stable. Learning how these groups decide who pairs up with whom is revolutionizing our understanding of gravity itself. It suggests that complex interactions at the very beginning of a star system's life dictate its long-term survival. If one of these tight subgroups were not perfectly balanced, the entire 10-star system would immediately unravel, slingshotting stars into the void like stones from a Roman catapult. Why do the systems that form these specific, stable subgroups survive, while others simply tear themselves apart? That is one of the deepest mysteries remaining in stellar physics. The secret to their survival lies in that gravitational hierarchy, but it does not explain how they were born in the first place. This brings us to discovery number 1, the impossible formation paradox. Current models of stellar birth simply do not allow for 10 massive stars to form successfully in such a tight neighborhood. When we try to simulate this event, the massive gravitational forces either cause the forming stars to spiral violently into one another, becoming one giant star, or they accelerate the smaller stellar cores outward, scattering them across the galaxy. Neither outcome results in a stable D10 system. Astrophysicists have proposed two main ideas to explain this gravitational defiance. The first is called hierarchical accretion. This suggests that the system forms small, stable binary pairs first, and then those pairs slowly attract other pairs or single stars over millions of years, building the system from the inside out. But this method is too gentle. It would take far too long, and the system would likely be torn apart by outside forces before reaching the count of 10. The second theory is the capture scenario. This imagines 10 stars forming separately in a dense, chaotic cluster, and then through multiple close gravitational encounters, they all end up accidentally bound together. It sounds feasible, except the sheer amount of energy involved in those capture dynamics would almost certainly cause stars to collide or burn out too quickly. Observing the clean, precise orbits of the genuine D10 system suggests there was nothing accidental about their birth. They seem to have been born exactly where they needed to be, defying both the gentle builders and the chaotic smashers. And this leads directly into discovery number 2, the birth cluster mystery. If these stars did not form slowly and they did not capture each other in a dense crowd, where did they come from? We usually find massive, young stars still nestled inside the giant clouds of gas and dust known as stellar nurseries or birth clusters. These nurseries are packed with hundreds of stars. But the Decuple star systems are rarely found there. In fact, many of them are discovered relatively isolated, miles away from any major star-forming region. This isolation poses a bizarre question. If they formed in a dense cluster like all other massive stars, something must have ejected them from that cluster immediately after their creation. To eject a system containing 10 entire stars, an immense slingshot force is required. The system would have to be accelerated so quickly that it maintains its internal stability while being thrown entirely out of its home system. No known gravitational mechanism is powerful enough to perform this kind of clean, precise eviction without tearing the D10 system apart in the process. It is as if some unknown force carefully picked up the finished 10-star structure and placed it in the empty darkness of space. Finding a stable 10-star system far from a nursery suggests that whatever dynamic created it was so violent it pushed the entire family away, yet gentle enough not to disrupt the delicate orbital ballet they perform. Something is missing from our current understanding of stellar ejection dynamics. Something must anchor the entire system together during these chaotic formations. This leads us to discovery number 3, the strange finding of gravitational resonances that seem to defy mathematical prediction. We learned earlier that these 10 stars organize themselves into tight subgroups, say 3 stars here, 3 there, and 4 in the third group, all orbiting a common center. For a system to remain stable over millions of years, the orbital periods of these subgroups must be in a perfect and simple ratio. For example, one star might complete 2 orbits for every 1 orbit of another star. This is called orbital resonance, and it is the key to stability in any multi-body system. In systems with only a few stars, these resonances are fairly easy to calculate and predict. However, in the D10 systems, the complexity explodes. With 10 massive bodies and dozens of internal interactions, the mathematics describing their stability becomes impossibly complex. If even one of the 10 stars were slightly off in its timing, the whole system should instantly destabilize, creating a deadly cascade of collisions. Yet the systems we observe are remarkably stable. Astronomers have found that the D10 systems operate with simple, high-order fractional resonances, ratios like 7:3 or even 9:4, that should not provide long-term stability. The margin for error is infinitesimally small. It is as if these stars are not just following the rules of gravity, but following a choreographed script where every single movement is timed to the millisecond. How do 10 stars, each forming with slightly different masses and speeds, end up adopting these precise, mathematically difficult orbits that prevent total collapse? It suggests there is either an unknown damping factor at work, absorbing the erratic movements, or that the initial formation process is so finely tuned it borders on deterministic perfection. It raises the question, are these systems truly stable, or are we just witnessing the brief eye of a massive gravitational storm that is destined to erupt in a cataclysmic collision one day? Trying to model the stability of 10 stars at once requires solving the infamous n-body problem. This is a computation nightmare that even our most powerful supercomputers struggle to manage. Discovery number 3 is the evidence that these Decuple systems thrive on mathematical unpredictability. For a normal solar system, orbital resonance is key. This happens when the time it takes two bodies to complete an orbit is a simple whole number ratio, like 2 to 1 or 3 to 2. When this perfect synchronization occurs, the gravitational influence remains predictable and the system stays orderly. In the D10 systems, however, we see something bizarre. They maintain what astronomers call quasi-stable orbits. This means they are stable enough to survive for billions of years, but the math predicting that stability is hopelessly complex. When scientists run in-body simulations for these stellar families, using the exact masses and speeds observed, the equations continually predict that the system should quickly collapse or violently eject several stars. Yet the real systems remain intact. Take, for example, the hypothetical D10 called the Kraken formation. According to our models, a slight gravitational nudge from the outer 4 stars on the inner triple group should cause the entire inner group to spiral inward, resulting in massive stellar mergers within a few million years. But the Kraken formation, or systems like it, continues its bizarre celestial waltz. This suggests that the systems are not operating on the basic, simple integer ratios that we require for stability. Instead, their resonances appear to be chaotic and highly fractional, almost like constantly shifting the gears in a 10-speed bicycle to prevent the chain from falling off. The sheer improbability of 10 stars randomly adopting such precise, chaotic timing has led some physicists to a wild, yet compelling conclusion. Could these systems be stabilized by something invisible? Is it possible that these Decuple star systems contain significant amounts of concentrated, yet unseen dark matter that helps damp down the gravitational chaos, acting like an invisible anchor preventing total collapse? Could it be possible that dark matter is the secret gravitational glue holding these 10 stars together? That is a truly compelling thought, but the mystery deepens when we examine the actual shape of their orbits. Discovery number 4 reveals the incredibly strange finding of hyper-eccentric outer orbits. For any star system to survive, we usually expect the orbits to be close to circular, especially for the stars at the very center of the hierarchy. If the path one star takes around another is too stretched out or eccentric, it risks coming too close to a neighboring star, triggering a catastrophic gravitational fight. Yet the outermost stars in the D10 systems defy this rule completely. They follow paths that are wildly stretched and elongated, like cosmic rubber bands that have been pulled almost to their breaking point. Astronomers use a measurement called eccentricity, where 0 means a perfect circle and 1 means a completely open, non-repeating parabola. Most stable systems rarely exceed an eccentricity of 0.2. But the outer components of the Decuple systems often boast eccentricities as high as 0.8 or even 0.9. Imagine a star on a path that takes it within a few million miles of its inner neighbors at one point, and then slingshots it out into the deep, cold blackness for millions of miles before it returns. This hyper-eccentricity should be impossible because the gravitational influence of the other 9 stars should quickly force that orbit to circularize, or worse, tear that star out of the system entirely. Why do these orbits remain so dramatically stretched? One theory suggests this stretching is a necessary countermeasure. The eccentric orbit allows the outermost stars to quickly pull away from the dense gravitational center, reducing the time they spend in the danger zone where collisions or ejections are most likely. It is a terrifying high-speed risk calculated to minimize long-term exposure. The system only survives because these outer members keep their distance most of the time. But the precision required to maintain these near-parabolic loops without being lost to the void is astronomical. It is a cosmic game of chicken, where an immense system keeps its most vulnerable members hanging on by the barest thread of gravity. If the timing of that slingshot is off by even a fraction of a degree, the entire 10-star family collapses. The system only survives because these outer members keep their distance. Most of the time is a crucial observation. Discovery number 5 builds directly on this by looking precisely at those hyper-eccentric orbits. While the innermost stars of these 10-star families often have nearly circular paths, tracing neat, predictable loops around each other, the outermost components are entirely different. These outlying 4 or 6 stars are on an orbital knife edge. Their paths are wildly stretched out and then swing violently close to the center of mass before they are flung out again. Think of it like a cosmic slingshot that repeats endlessly. Most of the time, the outer stars are traveling slowly through the darkness, far away from the gravitational pull of their 9 siblings. But then the momentum pulls them back, and they scream past the crowded center, taking milliseconds to traverse a space that would take a planet years to cross. This extreme orbit is measured by its ellipticity. If a stable planet's orbit is like a slightly squashed circle, these outer stellar orbits are more like extreme ovals, almost straight lines that curve sharply at the end. This constant high-speed, close-range interaction makes the stability of the entire system unbelievably fragile. Inside this chaotic dance, the prospects for stable planets are bleak. If any celestial body were trying to orbit one of these hyper-eccentric stars, it would experience wildly fluctuating gravity. One moment, it will be bathed in the heat and light of 10 suns passing closely overhead, and the next, it will be pulled into the deep freeze of interstellar space. These massive gravitational shifts would create extreme environmental changes, tearing at the internal structure of any orbiting world. It is the ultimate challenge to planetary stability and an environment where life as we know it is likely impossible. This chaotic slingshot mechanism might keep the 10 stars from collapsing, but it utterly destroys the possibility of a calm, habitable zone. It further reinforces the idea that these D10 systems are designed for stellar survival, not for nurturing planets. This chaotic slingshot mechanism introduces a terrifying dynamic we call star swapping. Discovery number 5 reveals that the makeup of the inner 3-star group is not permanent. Within the gravitational ballet of these 10 suns, the extreme eccentric orbits of the outer stars can trigger a phenomenon where one of the tightly bound inner stars is violently ejected and replaced by another, previously outer star. Think of the inner stable group as a protective pocket and the outer 7 stars as predators circling that pocket. Every few million years, or possibly even every few 100,000 years, the immense gravitational pull of a passing outer star disturbs the delicate balance of the inner trio. This disturbance acts like a cosmic wrecking ball, causing the least massive of the inner stars to be kicked out entirely, often flung far into the outer reaches of the system, or even ejected into interstellar space. Simultaneously, the star that caused the disruption is captured and settles into the newly vacated inner orbit, becoming part of the core stable unit. This star-swapping event is a dramatic gravitational reshuffling. The stars effectively trade places, maintaining the count of 10 stars and preserving the overall structure of 3, 3, and 4, whatever the configuration is. But the identities of the stars in the stable group change. This instability means that the systems we observe today are not the exact same systems that formed billions of years ago. They are constantly exchanging members, a kind of ruthless stellar democracy where only the fittest, most gravitationally compliant stars earn a place in the stable center. This discovery fundamentally challenges our view of star systems as static, predictable entities. It makes them seem more like a deadly, ever-shifting gravitational game of musical chairs. The implications are staggering, especially when considering the sheer amount of energy released during a star swap. It suggests that even the seemingly stable D10 systems are ticking time bombs, periodically undergoing massive gravitational convulsions just to survive. The actual mechanism of star swapping is less a collision and more a slow, consistent betrayal of gravity. Discovery number 5 highlights the observed phenomenon where stars subtly but consistently swap orbital allegiance over enormous timescales. These Decuple systems are almost always structured as nested binaries, meaning you have pairs of stars orbiting each other, and those pairs might orbit a triple core, which then all orbits the center of mass. This nesting creates a delicate balance. What astronomers witness is that over millions of years, due to external gravitational perturbations from the other 6 or 8 stars, a single star might transition its orbit entirely. For example, a star that has been stably orbiting star for 50 million years might slowly find itself being pulled more strongly by star B, and eventually it switches partners entirely. It is a slow, methodical orbital divorce. This switch is not violent, it is gradual, lasting several million years, and the star smoothly transitions its allegiance from one primary body to another. This change implies a level of systemic instability that utterly shatters our ability to make long-term predictions about these systems. We often think of star systems as operating on timescales of billions of years, remaining static and unchanged. But for the D10 systems, the cast of characters orbiting the core is constantly shifting. They are not merely surviving chaos, they are using it. Every star swap is a gravitational fine-tuning event, allowing the system to adjust to slight changes in mass or energy distribution from the surrounding universe. If the system did not have this ability to recalibrate by swapping partners, the slight imbalances that are inevitable in a 10-body system would compound over time, leading quickly to the catastrophic collapse that theory predicts. This dynamic ability to reshuffle the decks suggests that the stability of these systems is not a fixed state, but a continuous, active process. It raises the alarming question of whether any star system, even our own stable solar system, is truly fixed, or if everything in the universe is constantly flirting with total gravitational rearrangement. If the stability of these 10-star systems is a continuous, active process, what is powering that impossible longevity? Discovery number 6 reveals the deep perplexity of the missing mass conundrum. When astronomers calculate the total gravitational force required to keep 10 stars locked in their bizarre, chaotic orbits, the numbers simply do not add up. They calculate the total visible mass, which is the combined weight of all 10 stars, and then they compare that figure to the amount of gravitational pull needed to prevent the system from flying apart. In almost every D10 system observed, the gravitational pull required is vastly greater than the visible mass can account for. This gap suggests that there is a significant amount of invisible, non-stellar mass embedded within the system. We are not talking about a few dusty comets or small planets. We are talking about the equivalent of 3 to 5 extra suns worth of mass that is completely unseen. This is the missing mass conundrum. Where is this immense gravitational anchor hiding? One theory, as we touched on earlier, suggests that these systems are massive reservoirs of dark matter, pulling in the exotic, invisible substance and using its gravitational influence to maintain structural integrity. Dark matter does not interact with light, making it perfectly invisible, yet it exerts a powerful gravitational force. If this theory is true, these Decuple star systems might be the largest known dark matter batteries in the galaxy, deliberately maintaining stability through exotic physics. Another possibility is that the system contains a massive amount of cold, non-luminous gas and dust that has resisted collapsing into stars. This would be a giant reservoir of failed stellar material, incredibly dense and heavy, yet too cold to emit light. The implications are stunning. Either these 10-star families are stabilized by the most mysterious substance in the universe, dark matter, or they contain gigantic masses of material that defies the usual rules of stellar formation. The fact that the most complex star systems in the universe require 5 times the visible mass just to survive changes everything we thought we knew about gravitational balance. The missing mass is not just an astronomical curiosity, it is a statement that we are blind to fundamental components of these systems. If it is not dark matter, then discovery number 6 suggests we must look for dead stars. The sheer gravitational power emanating from a D10 system implies that perhaps the stars are not the only large bodies present. Instead of invisible gas or exotic dark matter, what if these systems are hiding the remnants of their own violent past? When 10 massive stars form close together, the intense gravitational environment means that some of them will end their lives much faster and more dramatically than our own sun. These spectacular deaths leave behind stellar remnants, the silent dark corpses of once bright stars. We are talking about white dwarfs, neutron stars, and even small stellar mass black holes, all tucked silently within the system's complex gravitational architecture. These remnants are incredibly heavy, packing the mass of a sun or more into a sphere the size of a planet or even smaller. They exert an immense gravitational pull, yet they emit almost no light, making them virtually invisible against the blinding glare of their 10 living siblings. The core centers of these decuple systems might not just be stellar nurseries, they could also be sprawling gravitational cemeteries. Imagine trying to find a soot-blackened marble in a bonfire of 10 suns. The challenge is immense. The energy output of the 10 luminous stars is so vast that finding a single white dwarf, much less a neutron star or black hole, requires incredibly sensitive instruments looking for the barest gravitational whispers. Astronomers are now actively searching for the telltale effects of these dark anchors, such as subtle wobbles in the orbits of the visible stars or brief flashes of X-rays emitted as material falls toward a hidden black hole. If these massive remnants are indeed the missing mass, it means the total number of bodies in a D10 system is not 10, but possibly 15 or 20, most of them dead. This changes the entire complexity of the orbital mechanics, transforming an already impossible dance into an even more baffling ballet of the living and the dead. If the missing mass suggests these systems hide dead stars, then what about the material that did not even manage to form into anything large? Discovery number 7 points to the astonishing existence of planet-sized asteroid fields within the most crowded parts of the D10 systems. We are not talking about a modest collection of space rocks like our asteroid belt. We are talking about colossal belts of debris, rubble, and planetesimals that collectively weigh as much as an entire small planet. These belts are crammed into the narrow, relatively stable lanes between the orbiting subgroups of stars. They create a terrifying, continuous ring of destruction. The gravitational environment of 10 competing suns means that any material left over from the formation process is constantly being pushed, pulled, and kneaded by immense tidal forces. This gravitational kneading prevents the material from ever coalescing into a stable planet, yet also prevents it from being ejected entirely. The result is a massive, dense ring of material, sometimes hundreds of millions of miles wide, where objects constantly collide at incredible speeds. Imagine an asteroid belt where every rock is moving 5 times faster than normal, and the entire belt is being bombarded by the gravitational pulses of 10 overhead suns. These fields are so dense that they absorb light and heat, actually contributing to the missing gravitational mass that astronomers noticed earlier. They act as a kind of gravitational shock absorber for the system, absorbing the violent energies that would otherwise destabilize the stellar orbits. But their presence raises a crucial question about the sheer inefficiency of star creation in these environments. The D10 systems are so massive and so chaotic that they seem to waste an enormous amount of planetary material, shredding it into these colossal, life-extinguishing fields. The raw materials for stable planets exist, but the gravitational environment is simply too severe to allow them to form. It suggests that these 10-star systems are not just hostile to life because of the light and heat, but because they are physically incapable of forming an orderly planetary system, trapping all the building blocks in a continuous, deadly gravitational blender. The sheer gravitational violence of a D10 system traps stellar material, turning potential planets into pulverized rings. Discovery number 7 confirms these star systems are littered with massive, kilometer-thick superbelts of debris. These are not the modest collections of rock found between Mars and Jupiter. We are talking about colossal agglomerations of dust and rock concentrated at specific, narrow zones within the system. These zones are usually the gravitational sweet spots, points of equilibrium called Lagrange points, or the stable gaps between the primary stellar subgroups. The total mass contained in one of these belts can easily equal that of a small, cold planet like Mars or even Earth, yet they consist entirely of trillions of small rocks and dense dust clouds. Why do these massive amounts of material never fully coalesce into a single, cohesive world? The answer lies in the constant, relentless gravitational shearing forces exerted by the 10 nearby suns. When a small planet begins to form, gravity pulls all the material inward, creating a single sphere. But in a decuple system, that fragile forming planet is constantly being stretched, squeezed, and pulled in multiple directions by the tidal forces of 10 massive bodies. It is like trying to bake bread dough while 10 different hands are trying to tear it apart simultaneously. The material is compressed enough to form these incredibly dense, massive rings, absorbing huge amounts of light and contributing to the missing gravitational mass. But it can never hold its shape long enough to achieve true planetary status. Instead, the material is trapped in a perpetual state of energetic rearrangement, constantly colliding, grinding, and compacting without ever settling down. This suggests that the D10 systems are not only hostile environments for existing planets, they are fundamentally incapable of nurturing new ones. They are the ultimate stellar environments that prioritize the survival of their stars over the creation of worlds, trapping the very building blocks of life in a cosmic, endless traffic jam of deadly pulverized rock. The ultimate challenge for stability in a 10-star family is not just gravity, but stellar energy. Discovery number 8 highlights the staggering problem of extreme stellar wind interaction. Every star, including our Sun, constantly blasts vast streams of charged particles into space. We call this the stellar wind. In a single star system, this wind flows outward, unimpeded. But imagine 10 massive stars, all packed closely together, each one trying to assert its own solar dominance with its own high-speed particle stream. The Decuple systems become environments of unimaginable turbulence where 10 stellar winds collide, creating continuous, violent shock waves. Picture 2 fire hoses aimed at each other, but now multiply that by 5. The kinetic energy released when these 10 massive streams of charged particles smash into one another is astronomical. Instead of smooth, predictable flows of radiation, the system is filled with chaotic, shifting walls of plasma and magnetic fields. This conflict of solar power generates extremely high-energy radiation, particularly powerful X-rays, as the superheated gases slam together. These colliding winds create massive magnetic eddies and plasma bubbles that are constantly expanding and collapsing. These magnetic bubbles act like giant cosmic pressure cookers. This chaotic internal environment is far more violent than the gravitational forces alone. The sheer pressure generated by these interacting winds could theoretically disrupt the fragile orbits of the interstellar subgroups, pushing them slightly off course and accelerating the system toward collapse. Yet the D10 systems somehow manage to process this energy without instantly tearing themselves apart. Astronomers believe the massive, invisible debris rings and potentially the dark matter reservoirs we just discussed might be crucial here. These dense, cold masses could be acting as magnetic sponges, absorbing the worst of the stellar wind shock waves, effectively shielding the orbital mechanics from the intense pressure. The very existence of these star families suggests that nature has found a way to manage 10 simultaneous solar storms, a level of energetic control that we are only beginning to comprehend. The constant clash of 10 stellar winds transforms these systems into extreme cosmic pressure cookers. This is the reality of discovery number 8, the observation of incredible turbulence and heating in the surrounding material. Every single one of the 10 suns is spewing out a supersonic torrent of charged particles, a solar wind that travels faster than sound. In a decuple system, these 10 streams collide head-on in what is known as a wind-wind interaction zone. The result is not a gentle mingling of air, but a series of continuous, violent shock waves that ripple throughout the entire system. When these particle streams smash into one another, the energy is instantly converted into heat, skyrocketing the temperature of the plasma to millions of degrees Celsius. Astronomers can map these zones by looking for the emitted X-rays, and the results show sprawling regions of superheated gas that extend far beyond the stars themselves. This turbulence is constantly churning the system's interior, creating massive magnetic fields that shift and distort the gravitational environment. This intense energetic chaos has 2 dramatic consequences. First, it profoundly affects the longevity of the stars themselves. These continuous plasma shocks slowly strip away the outer layers of the stars at an accelerated rate, causing them to burn through their fuel much faster than a star in a lonely single system. The stars in D10 systems might look young, but they are metabolically racing toward their deaths. Second, this intense high-energy environment makes it virtually impossible for the system to retain lighter, more volatile elements. The superheated plasma strips away hydrogen, helium, and any other gas that tries to settle, actively clearing the system of the very elements needed to form gaseous giant planets or to sustain long-term stable atmospheres. This explains why the star systems are mostly surrounded by pulverized rock and dense material rather than vast, calm gas clouds. The chaotic energy generated by the warring stellar winds acts like a celestial blow dryer, constantly stripping away the lighter elements, ensuring that only the most dense, electromagnetically neutral material can remain anchored within this stellar maelstrom. The continuous flow of violence and energy in these systems creates something entirely unexpected outside their boundaries. Discovery number 9 reveals a bizarre phenomenon known as the tidal tail anomaly. When we look at a D10 system, we do not just see 10 stars in isolation. We see the dramatic, smeared evidence of a gravitational battle being fought and lost. A tidal tail is a long, faint stream of stars and gas that is violently pulled away from a galaxy or star cluster during a close gravitational encounter. Think of it like cosmic smoke trailing behind a speeding car. For a galaxy, this is common. For a single star system, it should be impossible. Yet, astronomers have observed long, thin plumes of stellar material streaming outward from several Decuple star systems, stretching hundreds of light years into the void. These are the tidal tails of a star system. These plumes consist of stars, cold gas, and debris that have been stripped away from the main gravitational core by the immense tidal forces generated by the 10 suns. The sheer amount of gravitational energy required to rip a single star or a significant mass of gas out of the system and stretch it into a thin, cohesive line is staggering. It suggests that the combined, fluctuating gravity of the 10 stars is so extreme that it can tear the system's own structure apart while simultaneously holding the 9 remaining stars together. The stars and material in the tail are not ejected randomly. They are pulled in precise, predictable arcs, an almost elegant display of destruction. This anomaly confirms that while the inner core of the D10 system is engaged in a stable, if chaotic, ballet, the outer fringes are relentlessly being pulverized and stretched. It is the signature of a system that is constantly fighting its own gravitational nature, bleeding out material to sustain the stability of its core. Could these visible tidal tails be the only way the system sheds excess gravitational energy, dumping the unstable material into the cosmic darkness to ensure the survival of the center? The tail is a visible, undeniable sign that the system is not perfectly balanced. It is constantly self-correcting through violent ejection. The streaming tidal tails we just discussed hold secrets that go beyond mere gravitational ejection. This brings us back to discovery number 9, a strange finding that challenges our understanding of how gas and dust behave in space. These massive plumes of stellar material are not simply messy leftovers. They are highly organized, incredibly long ribbons of gas and dust stretching out from the Decuple star system, often for hundreds of light years. The real mystery is why these tails persist. In the cold vacuum of interstellar space, thin streams of ejected material should quickly dissipate. The gas molecules should spread out, scattering into the void like smoke in an open room. Yet the tidal tails observed near D10 systems maintain their structure, remaining coherent and ribbon-like over immense distances and vast cosmological periods. It is as if they are being held together by an invisible sheath. This surprising stability suggests a relatively recent, profoundly violent event shaped these tails, such as the initial chaotic collapse of the stellar nursery or a close, terrifying brush with a neighboring star cluster. If the system had a close encounter with another cluster, the gravitational shear could pull material away in a long stream, but that stream should still break apart over time. The fact that the tails remain intact suggests that the D10 system itself is responsible for locking down this escaping material. Could the solution lie in system-wide magnetic fields? The intense and continuous collision of 10 stellar winds, which we already discussed, generates sprawling, incredibly powerful magnetic fields across the entire star system. These magnetic fields could be acting like gigantic cosmic wires, running along the length of the tidal tails and physically containing the charged gas and dust within them. Essentially, the material is trapped in a magnetic tube, unable to disperse into the vacuum. If this is true, the D10 system is not just a gravitational wonder, it is an energetic machine that uses its internal plasma chaos to structure and manage the material hundreds of light years away. This magnetic stabilization would mean the tidal tails are the constant, visible signature of the system shedding excess energy and maintaining its own internal balance. It is a stunning display of cosmic self-regulation, using magnetic forces to prevent the complete gravitational unraveling of its own material. The violent magnetic energy generated by these systems shows up in an entirely unexpected way. Discovery number 10 is the observation of truly anomalous X-ray emissions surrounding every known Decuple star system. X-rays are usually a sign of extreme heat or highly energetic processes, like gas falling into a black hole or massive stellar flares erupting from a sun. While we expect some X-ray activity from 10 young, massive stars, the observed emissions are hundreds of times stronger than predicted by standard models. These D10 systems are not just glowing, they are screaming with high-energy radiation. This intense X-ray output is not coming from the surface of the stars themselves. Instead, the X-rays originate in the vast turbulent regions between the stellar subgroups. This confirms that the primary source of extreme energy is not the nuclear furnaces of the stars, but the chaotic internal environment we call the wind-wind interaction zone. When those 10 stellar winds smash together, the particles are accelerated to such incredible speeds that the resulting shock waves heat the plasma to tens of millions of degrees, releasing a continuous torrent of high-energy X-rays. Think of it less as 10 stars shining and more as 10 stars creating a gigantic, superheated cosmic pinball machine within their gravity well. This constant high-level X-ray bombardment has profound implications for anything trying to survive inside the system. Any forming planet that manages to avoid being pulverized by the gravitational shears will be instantly sterilized by the radiation. The X-rays would strip away all atmosphere, break down complex molecules, and prevent any attempt at life from even beginning. Furthermore, this intense energy signature is so powerful that it makes studying the systems themselves incredibly difficult. The X-rays can contaminate sensitive measurements needed to determine the exact masses of the constituent stars or the precise shape of their orbits. It is the system itself fighting back against observation, shrouding its deepest secrets in a continuous, blinding veil of high-energy radiation. The presence of this anomalous radiation suggests we are dealing with a type of stellar physics that involves processes far more energetic than mere fusion. The blinding veil of X-rays around these Decuple systems hides incredible secrets about energetic physics. Discovery number 10 is confirming that the radiation is not merely a byproduct of 10 young suns. It is a signature of constant war. Normal stars produce X-rays from hot coronal gas, but the X-ray output from a D10 system is hundreds of times greater than the combined output of 10 isolated stars. This energy is being generated in the space between the stellar groups, specifically where the magnetic fields of the entire stellar family clash. Every sun in the system possesses a massive, invisible magnetic field, a magnetosphere that stretches far out into space. As these 10 stars orbit one another at high velocity, their magnetospheres are forced to interact violently. Lines of magnetic force snap and reconnect in a continuous, explosive process. Think of it like 10 powerful rubber bands constantly stretching and breaking, generating immense bursts of energy. This magnetic chaos accelerates charged particles to near light speed, causing them to slam into surrounding gas and dust. The resulting shocks heat the material instantly to millions of degrees, creating the intense X-ray hotspots that astronomers now observe. This means the central region of a D10 system is essentially a gigantic particle accelerator powered by magnetic field lines. This constant lethal radiation is the ultimate sterilizing agent. It ensures that even if stable planets formed in the quieter orbital gaps, the relentless X-rays would instantly destroy complex molecular structures. Any planet orbiting here would have its atmosphere stripped away in short order, leaving behind a cold, radiation-blasted hulk. The intense X-ray activity is a vital clue that the stability of these 10-star systems must involve more than just gravity. It requires a continuous, massive process of energetic self-regulation, using magnetic forces and violent particle acceleration to manage the unimaginable pressures within the star system. The incredible energy of these Decuple systems means their stars are not aging normally. Discovery number 11 reveals the terrifying reality of star-eating vampire pairs at the core of these 10-star families. Astronomers have found that within the tightly bound subgroups, the stars are often radically different in age and size, a situation that should not happen if they all formed at the same time. The explanation lies in a murderous process called mass transfer. In many D10 systems, the inner core is dominated by a binary pair consisting of a large, hot blue star and one smaller, less evolved companion. The larger, more massive star is the vampire. It uses its immense gravitational pull to continuously strip away hydrogen and helium from the atmosphere of its smaller sibling. This constant theft of material has profound consequences. The vampire star is constantly rejuvenated by this new fuel. It stays hot, massive, and intensely luminous, far longer than it should according to its age. Meanwhile, the smaller star, the victim, is slowly being drained of its essential fuel source. It becomes a shrunken, colder remnant of its former self, evolving into a strange, low-mass object that appears much older than its true age. This creates the age paradox where two stars, born simultaneously, look vastly different in their evolution. This mass transfer process is not gentle. It is a violent, spiraling dance that generates even more of the X-ray radiation we discussed and further destabilizes the precise orbits of the other 8 stars. The vampire star's mass is constantly increasing, altering the gravitational balance of the entire system, while the victim star is shrinking, adding to the chaotic instability. The D10 systems are not just stable in spite of chaos. They are stable because they have incorporated mechanisms of controlled destruction into their very core. This continuous cannibalistic feeding allows the star system to recycle stellar material and manage the overall mass distribution, keeping the system in a relentless state of gravitational flux. It shows that survival in a 10-star family sometimes means literally consuming your neighbors. Survival in a 10-star family sometimes means literally consuming your neighbors. The core of these unstable yet enduring systems is frequently dominated by this horrific ballet. Discovery number 11 reveals that many of the tight stellar subgroups are built around what astronomers call vampire stars. This is not just a metaphor. Within a closed binary pair, one star is slowly drawing the life force from its mate. Typically, the vampire is a very compact, dense stellar remnant, such as a white dwarf or a subgiant star. It uses its intense, focused gravity to siphon hydrogen and helium from the surface of its large, less dense companion. The extreme gravitational pressures inside a D10 system stabilize this ruthless transfer of mass, accelerating the process beyond normal expectations. As the smaller, dense star gorges on the new fuel, it becomes unnaturally bright and unstable, often shining with the luminosity of a much younger star. Meanwhile, the victim star is being slowly stripped of its outer layers, sometimes even being reduced to a bare stellar core. This cannibalistic action constantly destabilizes the gravitational balance of the entire Decuple system, yet it also provides a perverse kind of stability by allowing the system to shed excess mass through the violence of the transfer process. It is a controlled bleed where one star sacrifices itself to maintain the fragile orbital geometry of the whole. This relentless mass transfer generates immense instability and explains why we see massive X-ray flares and bizarrely mismatched stellar pairs in the same orbital neighborhood. But what happens when one of these massive, cannibalistic stars finally reaches the end of its life in a cataclysmic explosion? That catastrophic end leads directly to discovery number 12, the incredible finding of asymmetrical supernova. When a massive star dies, it detonates in an event called a supernova, releasing more energy in a few seconds than our sun will emit in its entire 10 billion-year lifespan. This explosion should be symmetrical, a spherical blast wave radiating outward like a cosmic balloon popping. Yet when astronomers observe the nebulas and remnants left behind by supernova in D10 systems, they consistently notice that the resulting cloud is violently lopsided or asymmetrical. The blast wave itself appears to have been pulled forcefully to one side. Imagine setting off a firework only to have the explosion immediately yanked sideways by an unseen force. This bizarre warping of a stellar death explosion is a profound mystery. Astrophysicists believe the culprit is the immense concentrated gravitational drag exerted by the star system's 9 remaining siblings. As the supernova blast wave expands outward, the combined gravitational pull of the 9 incredibly massive stars acts like a gigantic cosmic hand, tugging on the material and distorting the explosion into an egg shape or a massive smear. The gravitational pressure is so extreme that it can physically mold the energy and matter released by a collapsing star. This asymmetry is not just a visual curiosity. It suggests that the immense fluctuating gravity of a decuple system can interfere with the fundamental physics of stellar death. This distortion should alter the direction and speed of the stellar remnant left behind, likely a neutron star or a black hole, adding yet another unpredictable, highly massive body to the existing chaotic gravitational ballet. The existence of these lopsided supernova remnants provides tangible evidence that the D10 systems are environments of truly extreme physics, where even the largest explosions in the universe must bend to the will of 10 competing gravity wells. The explosion of a dying star is not the only thing distorted by these immense gravity wells. Discovery number 13 reveals the baffling truth of the tilted ecliptics puzzle. In our solar system, all 8 major planets orbit the sun on a relatively flat plane, like marbles rolling on a dinner plate. We call this the ecliptic. This alignment is a direct result of the system forming from a spinning disk of gas and dust. In all stable star systems we know, the planets, if they exist, and the stars themselves, tend to orbit along a shared, flat plane. But the decuple star systems actively reject this fundamental order. Astronomers mapping the orbits of the 10 central stars have found that their orbital planes are violently misaligned, intersecting at steep, random angles. It is less like a dinner plate and more like 10 separate frisbees thrown haphazardly through the same small space. You might see one subgroup of 3 stars orbiting horizontally, while the adjacent group of 2 stars orbits vertically, cutting through the first group's plane at a 60-degree angle. This extreme misalignment is called a tilted ecliptic, and it is a profound mystery. If all 10 stars form from the same initial cloud of gas and dust, they should all be orbiting on a shared plane. The fact that they are not suggests that something dramatic and external warped their orbits almost immediately after they formed. One possible explanation involves the gravitational shearing forces during the system's eviction from its stellar nursery, the idea we discussed earlier. If the entire nascent D10 system was violently slingshotted out of its birth cluster, that immense asymmetrical force could have twisted and tilted the orbital planes of the individual stellar groups like a cosmic torsion spring. Alternatively, the tilted ecliptics could be the result of the star swapping process we detailed earlier, where a star is captured from a vastly different orbital plane and violently integrated into the system. Whatever the cause, this chaotic orbital geometry means that the gravity within a D10 system is not just strong, it is constantly changing direction. A planet orbiting here would not only be pulled inward and outward, but also constantly yanked up and down, making it impossible for stable planetary orbits to exist in 3 dimensions. This geometrical chaos is a powerful indicator that the stability of these 10-star families is a dynamic, tortured balance, where order is constantly being sacrificed for sheer survival. The geometric chaos of a tilted ecliptic is one of the most unexpected findings in these 10-star families. Discovery number 13 confirms that the orbital planes of the nested star groups are often wildly misaligned, sometimes by as much as 90 degrees. In a typical star system, all of the stars and planets orbit the gravitational center on a single shared plane. This is the natural outcome of the formation process, where a giant, spinning cloud of gas and dust flattens out into a disk, and everything that forms within it spins in the same direction. The D10 systems simply ignore this rule entirely. Instead, astronomers see smaller subgroups, say a pair of stars orbiting close together, and their orbital plane is tilted 40 or 50 degrees relative to the orbital plane of the core triple star group they are revolving around. This violent misalignment means the stars are not just pulling on each other horizontally, they are constantly exerting immense forces vertically as well. Imagine trying to keep 10 different pendulums swinging in the same room without any of their paths crossing. In a decuple star system, the paths cross constantly, but the stars somehow miss each other. This geometry of chaos is impossible to achieve through quiet, gradual formation. It is a signature of tremendous external violence. Astrophysicists propose that this extreme tilt could only be achieved if the D10 system suffered a devastating gravitational shock early in its life. Perhaps a massive rogue star or even a dense globular cluster passed terrifyingly close to the nascent system, twisting the entire configuration like a piece of cosmic taffy. This close encounter would have ripped at the edges of the forming star groups, forcibly tilting their individual orbits before the system had a chance to fully stabilize. Another compelling theory suggests that the tilt is a legacy of the initial formation paradox we discussed earlier, implying that the 10 stars did not form quietly, but merged from several smaller, chaotic stellar fragments that collided and violently integrated, each impact adding a new, unpredictable, angular momentum to the mix. The fact that these systems maintain stability despite this three-dimensional gravitational jolt is perhaps the most impressive feat of physics yet. The tilted ecliptics puzzle demonstrates that the gravitational rules are not just bent in D10 systems, they are dramatically renegotiated by some initial cataclysmic event that fundamentally reshaped their entire geometry. The sheer violence of a tilted ecliptic requires an equally powerful stabilizing force. Discovery number 14 points to the astonishing complexity of the magnetic fields in these decuple systems. We are not talking about a simple north and south pole like on Earth or even our sun. Imagine 10 massive stars, each spinning on its own axis, each generating its own immense magnetic field. Now shove them together into a confined, high-speed orbit where those magnetic fields are constantly twisting, merging, and fighting the fields of their 9 neighbors. The result is a system-wide magnetic architecture of unimaginable complexity. Astronomers use massive radio telescopes to map these fields, and what they see is baffling. Instead of a smooth, uniform field, they detect thousands of tiny, localized magnetic loops and knots throughout the system, like a tangled ball of luminous string. These individual magnetic fields are not canceling each other out as one might expect. Instead, they appear to be self-regulating, carving out magnetic channels and pathways through the plasma. They act as invisible traffic cops, directing the flow of charged particles and preventing the superheated plasma from simply overwhelming the stellar orbits. In fact, some physicists believe these magnetic channels are the true secret to the D10 system's stability. The magnetic pressure created by this tangled web might be physically pushing the stars into their precise, though chaotic, orbits. Gravity might be pulling them toward collision, but the magnetic fields are acting as invisible, powerful barriers, maintaining the necessary separation. This incredible magnetic scaffolding is vital because it manages the chaos that gravity cannot. It dampens the worst effects of those hyper-eccentric orbits and absorbs the energy from the wind-wind interaction zones, shielding the system from total collapse. Without this bizarre multipolar magnetic field complexity, the 10-star system would likely tear itself apart in a matter of centuries, rather than enduring over millions of years. This discovery suggests that the universe has methods of maintaining order that rely not just on gravitational force, but on the delicate, complex interaction of magnetic pressures on a scale we previously thought was impossible. This incredible magnetic scaffolding is vital because it manages the chaos that gravity cannot. The constant, brutal interaction of 10 stellar dynamos creates consequences that visibly affect the stars themselves. Discovery number 15 focuses on the baffling phenomenon of suppressed stellar activity. Every single star, including our sun, has magnetic features on its surface called sunspots, or in the case of other stars, star spots. These are regions where concentrated magnetic field lines suppress the outward flow of heat, making the spot appear darker and cooler. These magnetic complexities are also the source of solar flares, massive explosions of energy that shoot charged particles out into space. In a D10 system where magnetic fields are twisted and magnified by the extreme proximity, we would expect to see continuous, massive flares and star spots covering 90% of the star's surface. The reality is the opposite. Astronomers have found that the stars in the innermost, tight subgroups often display surprisingly low levels of both star spots and flare activity. Their surfaces appear unnaturally smooth and calm, almost as if they are magnetically paralyzed. How can 10 stars generating maximal magnetic fields and whose fields are violently colliding suddenly become so magnetically placid? One theory suggests that the continuous gravitational and magnetic shearing from the other 9 stars prevents the magnetic fields from organizing into the large, stable loops necessary to create sunspots. The magnetic field lines are constantly being torn apart and reformed by the tidal forces, preventing the concentration of magnetic flux that leads to a visible spot. Instead of a few large, organized spots, the magnetic energy is dispersed across the entire surface in thousands of tiny, invisible microflares. This magnetic suppression is a crucial element of the system's longevity. If the stars were constantly erupting in massive flares, the resulting energetic output would violently push against the delicate orbital balance, accelerating the entire system toward a rapid, chaotic collapse. This discovery suggests that the system has developed a mechanism to distribute and stabilize magnetic energy, trading large, catastrophic eruptions for a continuous, low-level discharge. It is a form of magnetic self-medication, where the overwhelming stress of the 10-star environment forces each star into a state of unnatural, life-saving calm. The overwhelming stress of the 10-star environment can force a star into a state of unnatural calm, but sometimes that stress simply kills a star outright, leaving a much darker presence behind. This leads us straight to discovery number 16, the genuinely bizarre finding of a Decuple system containing both a pulsar and a black hole. When astronomers talk about a star system, they usually mean 10 living, burning suns. But one specific D10 system, which we will refer to as the Chimera system, harbors something far stranger at its core. Tucked into one of the tight subgroups is a pulsar, the rapidly spinning, incredibly dense remnant of a massive star that died. Pulsars sweep beams of radio waves across space like a lighthouse, and their precise timing makes them invaluable clocks for astronomers. Orbiting the pulsar is a small, stellar mass black hole, an object so gravitationally powerful that nothing, not even light, can escape it. This means the Chimera system is not just 10 suns, it is 10 suns plus 2 stellar corpses that are still incredibly massive and gravitationally active. This presence of both a pulsar and a black hole in a confined space is astonishing. It means the gravitational landscape of the system is not only dominated by the light and heat of 10 stars, but also by the invisible, powerful pulls of these two dark gravitational giants. The black hole and the pulsar are in a closed binary orbit themselves, meaning their combined, intense gravity is constantly dragging and pulling on the other 8 suns in the system. The timing of the pulsar's radio pulses is itself distorted by the gravitational tides of the other stars, providing astronomers with an unprecedented opportunity to study how extreme gravity affects time and space. The fact that the entire 10-body system manages to remain stable despite harboring these two gravitational extremes is a profound testament to the system's ability to self-regulate. Imagine trying to balance 10 spinning tops, 2 of which are made of neutron star material and black hole material, and still maintaining the fragile overall arrangement. The existence of stellar remnants this massive and dense in a Decuple system confirms that the missing mass problem is likely solved by these dead stars. These gravitational anchors are the unseen forces holding the entire impossible dance together. The existence of dark, massive anchors is not a theoretical assumption. Discovery number 17 confirms the truly extreme case of the Chimera system, a Decuple family that defies all prior gravitational limits. This system is not just 10 suns orbiting one another. It is a family that includes both a rapidly spinning pulsar and a small, stellar mass black hole, both tucked deep inside the most crowded inner subgroup of 3 stars. Imagine the absolute gravitational nightmare this creates. A pulsar is a neutron star that spins with incredible precision, emitting a beam of radio waves that sweeps past Earth like a cosmic lighthouse beam. Since these pulses are timed to the millisecond, astronomers use them as the most accurate clocks in the universe. But in the Chimera system, the timing of that pulsar is constantly being distorted and warped by the immense, fluctuating gravity of the 9 other massive stars. Every time one of its sun or black hole neighbors passes close, the pulsar's timing is slightly delayed or accelerated by the gravitational drag, an effect predicted by Einstein's theory of general relativity. Tracking the pulsar's signal is like trying to measure the time on a watch that is constantly being yanked and pushed by 9 different hands. At the same time, the black hole, the second dark anchor, exerts a powerful but invisible pull on every other body in the system. Black holes are stealthy, they do not emit light, and we only detect them by observing the gravitational effect they have on their surroundings. In a single or binary system, tracing a star's wobble to find an invisible black hole is difficult enough. In a decuple system, the black hole's influence is completely masked by the noise of the 9 other massive bodies, making precise calculation almost impossible. The successful identification of both a black hole and a pulsar in the same 10-star system represents the absolute pinnacle of gravitational complexity. It confirms that the D10 systems are not merely stellar factories, they are laboratories of extreme physics where the most dense objects in the universe are forced to dance with each other, testing the limits of orbital stability. The survival of the Chimera system suggests that gravity itself is far more forgiving and adaptable than our current mathematical models allow. The sheer presence of black holes and pulsars makes 10-star systems seem utterly hostile to life, yet the universe has a way of surprising us. Discovery number 16 introduces the mind-bending possibility of temporary planetary habitability, or flickers of life. Within the chaotic gravitational environment, most of the system is constantly bathed in lethal radiation and extreme temperature swings. However, astronomers have modeled extremely specific, localized zones where stable conditions might exist for short periods. Imagine a planet orbiting one of the stars in the outermost subgroup. This star is on a hyper-eccentric, highly stretched orbit, meaning it spends 90% of its time flung far out into the darkness of the system, away from the gravitational turmoil and the searing X-rays of the core. During these long, distant excursions, the orbital environment around that single star becomes surprisingly calm. The gravity of the 9 other stars is diminished by distance, and the intense radiation fields are hundreds of times weaker. For a period of perhaps 500,000 to 1 million years, a planet orbiting this isolated sun could experience a relatively stable climate and atmosphere. This period is the flicker of habitability. It is a cosmological piece that is tragically short-lived. Eventually, the eccentric orbit pulls the star and its companion worlds back toward the crowded, violent core. As the star screams past the center of mass, the planet is instantly subjected to unimaginable tidal forces, overwhelming radiation, and intense wind-wind interactions that would vaporize its atmosphere and sterilize its surface. But the very existence of these tranquil interludes suggests that life, given enough time, might evolve to survive these massive environmental pressures. Could native life forms hibernate for 1 million years, waiting out the gravitational storm only to reawaken during the next brief flicker of calm in the cold, distant outer reaches of the Decuple system? This possibility challenges our fundamental definition of a habitable zone, transforming it from a static region into a constantly shifting, periodic opportunity for life. This brief window of warmth suggests where to look for the universe's hardiest life forms. Discovery number 16 explored the bizarre theoretical possibility of planetary flickers of life within these chaotic decuple systems. Now we dive deeper into what this means for extremophile survival. Due to those wildly stretched hyper-eccentric orbits, a frigid, icy planet in the outer regions of the system experiences the ultimate cosmic roller coaster. For millions of years, this planet is flung far out into the darkness, a frozen, desolate world where surface temperatures hover near absolute zero. Any water on its surface is solid, deep ice. Then the immense gravity of the core pulls the star and its companion planet back into the inner, crowded regions of the 10-star family. As the star swings violently past the center of mass, the planet is suddenly bathed in the heat and light of not one, but up to 10 suns simultaneously. This brief, intense thermal shock lasts for a few thousand years, enough time for the planet's surface ice to melt into liquid water. Crucially, the period of maximum heat is extremely short, meaning the water might avoid full vaporization and remain liquid long enough for complex chemistry to occur. This is the temporary planetary spring, a short-lived event where the conditions for life briefly exist. Once the star slingshots past the core, the planet is plunged back into the deep freeze, beginning its long, slow journey back to the outer darkness. Any life that could evolve here will be unlike anything we have encountered, requiring extreme resilience. Imaginative scientists have proposed extremophile life forms that spend millions of years in a state of suspended animation, frozen deep beneath the ice, only to revive for the few thousand years of liquid water, rapidly reproducing and evolving before the next deep freeze sets in. This kind of existence requires life to be incredibly robust, capable of withstanding massive radiation doses during the inner pass and surviving an absolute vacuum of cold during the outer journey. The implications are stunning. We might not need static, perfect habitable zones for life to exist. We might only need these brief, periodic geological moments of perfect chaos to kickstart evolution. The chaotic gravity of the Decuple system, the very force that should sterilize the worlds, might instead be creating a natural, cosmic trigger for life's most extreme forms. The chaotic gravity of a Decuple system does more than just rearrange stars and sterilize worlds. Discovery number 17 reveals that these systems act as massive, warped lenses, profoundly amplifying the light of objects millions of light years away. This phenomenon is called gravitational lensing. We know that any massive object, such as a galaxy or a star, bends the fabric of space-time around it. When light from a distant background source passes through this curved space, it is focused and magnified, much like light passing through a massive glass lens. In a single star system, this effect is subtle, but in the D10 systems, the effect is multiplied by the combined fluctuating mass of 10 suns, a black hole and possibly a pulsar, all packed into a tiny volume of space. The resulting gravitational field is not smooth and predictable. It is a highly textured, complex warp in space-time that astronomers call a multi-directional microlens. This complex warping allows the D10 systems to focus and magnify light from objects far deeper in the universe than we could ever observe otherwise. There are essentially giant, naturally occurring telescopes built entirely out of gravity. Astronomers utilizing this effect have been able to spot ancient galaxies and quasars that are far too faint to be seen with even the world's most powerful man-made telescopes. The Decuple system becomes a crucial intermediary, bending the faint light and amplifying it by factors of 10, 50, or even 100. The challenge is that the focus of this gravitational lens is not static. Because the 10 stars and their dark companions are constantly orbiting at high speed, the entire lens is perpetually shifting and wobbling. This means the amplification effect turns on and off suddenly, sometimes lasting only a few hours before the gravitational alignment collapses. Astronomers must race against time to capture data on the distant object before the stellar family waltzes out of alignment, plunging the background light back into invisibility. This discovery is a double-edged sword. While it grants us incredible glimpses into the early universe, it also confirms that the gravitational environment of these 10-star systems is so convoluted that it literally warps space and time, turning the system itself into a dizzying cosmic kaleidoscope. The warped geometry of space-time around a Decuple star system is not incidental. Discovery number 17 confirms the system is a cosmic magnifying glass, amplifying light from the deepest parts of the universe. Gravitational lensing occurs when a massive foreground object bends light from a background source, focusing it toward the observer. In most systems, the effect is subtle, a tiny smear or stretch on a background galaxy. But when you aggregate the mass of 10 suns, a black hole, and a pulsar into a single chaotic location, the lensing becomes profound and extreme. The total gravitational pull is so immense it creates a complex, textured warp in the fabric of space-time itself. This distortion acts as an accidental, natural telescope, allowing astronomers to see galaxies billions of light years away that would otherwise be entirely invisible. The light from these ancient background galaxies is bent and focused by the D10 system, making them appear hundreds of times brighter than they actually are. But this incredible tool comes with a massive caveat. Because the mass of the Decuple system is not static, the resulting image is highly distorted and often multiply-imaged. Instead of seeing one clear picture of a distant galaxy, astronomers will often see 4, 6, or even 8 separate stretched arcs of light, all originating from the same single source. These multiple images are caused by the light path being split and bent around the individual mass concentrations of the 10 suns and their dark companions. The light is literally taking multiple paths around the gravitational knots of the D10 system before reaching our telescopes. This complex distortion is both a blessing and a curse. While the magnification is incredible, deciphering the actual shape and nature of the distant object requires complex computational unwrapping of the distorted images. Furthermore, the light arcs are not stable. Since the 10 stars are constantly orbiting and star swapping, the entire lens is perpetually shimmering, causing the multiple images to fade, brighten, and shift position over periods of days or even hours. Astronomers race against the clock to capture data before the powerful gravitational lens winks out of alignment. This stunning discovery not only confirms the immense total mass of these systems, but also demonstrates how the chaotic internal arrangement literally convolutes space and time on a truly massive scale, turning the system into a dizzying gravitational machine. The baffling chaos of the Decuple systems holds one more profound chemical secret. Discovery number 18 reveals the strange finding of unusually low metallicity in these massive stellar families. Metallicity in astronomy simply refers to the amount of elements heavier than hydrogen and helium present in a star. Our Sun, for example, is fairly metal-rich. When a star system forms from a cloud of gas and dust, it inherits the chemical composition of that cloud. Massive stars, especially those that form in dense clusters, usually have higher metallicity because the stellar nursery has been contaminated by the remnants of earlier generations of stars that have already exploded and seeded the cloud with heavy elements like oxygen, carbon, and iron. Since D10 systems are so massive and so energetic, we would naturally expect them to be incredibly metal-rich. The reality is the opposite. When astronomers analyze the spectra, the light signature of the stars in these 10 sun families, they find them to be surprisingly pristine, containing a much lower concentration of heavy elements than expected for stars of their mass and age. This low metallicity is a huge puzzle. If these stars formed in a crowded, rich stellar nursery, they should be full of metals. This suggests two radical possibilities. The first is that the stellar winds, which we already established are violently colliding and creating X-rays, are so powerful that they are actively stripping away the heavier elements from the star's surfaces, preferentially removing them from the system over time. The second and more profound possibility relates directly back to the birth cluster mystery. If these stars are metal poor, it means they might have formed in a profoundly pristine, isolated environment that was protected from the chemical pollution of previous supernova. This would argue against the theory that they were violently ejected from a dense, chemically rich stellar nursery. Instead, it suggests that these 10-star systems are the result of an entirely unknown, specialized formation mechanism that occurs only in the most remote, chemically primitive reaches of the galaxy. They would be the ultimate stellar outliers, not just gravitationally, but chemically unique. The metal-poor composition means that any planets that might form in these systems will be predominantly rocky and small, almost entirely lacking the heavier elements like iron and nickel that create large, dense planetary cores. This lack of heavy metals in the available planetary building blocks further complicates the search for stable, Earth-like worlds in these chaotic stellar environments. The puzzle of low metallicity radically challenges our timelines for these cosmic monsters. Metallicity, the amount of elements heavier than hydrogen and helium, is the chemical fingerprint of a star. In astronomy, the stars in the core of these Decuple systems are surprisingly metal-poor. This means they are chemically primitive, containing very little iron, carbon, or oxygen. Finding metal-poor stars is usually a sign that they are incredibly old, belonging to the earliest generations of stars that formed before the universe had been sufficiently enriched by the explosions of prior, massive stellar deaths. Metal-rich stars like our Sun are considered second or third generation, forming in chemically polluted nurseries. The finding of low metallicity in these massive, high-energy D10 systems is entirely counterintuitive. Why would such chemically ancient, metal-poor stars form the most complex, gravitationally dynamic configurations known to the universe? We typically associate the formation of high-order, complex star systems like these with later, metal-rich generations of stars because the higher density of elements helps stabilize the formation process. If these stars are truly old and poor in metals, they should have been incapable of forming such a tightly packed, gravitationally extreme constellation. This suggests that the D10 systems are either far older than their bright, blue, energetic appearance suggests, or they formed from gas clouds that were somehow completely pristine and isolated from surrounding stellar enrichment. Imagine discovering a 1,000-year-old grandfather clock that was built using modern, precise, high-tech steel. The components simply do not match the expected age and complexity. The only way to explain this age and complexity mismatch is that the sheer gravitational pressure and chaotic dynamics of the D10 system formation process are so powerful that they can force primitive, metal-poor gas clouds to collapse into multiple, tightly organized stars. This would mean that the complexity of a star system is not dependent on its chemical richness, as previously assumed, but only on the localized perfection of the gravitational forces at play. This chemical anomaly provides a rare glimpse into the very earliest, most turbulent moments of star formation in the universe, suggesting that the complexity of these stellar monsters is a result of sheer, raw, uncompromised gravity. The chemical composition of these 10-star systems is not static either. Discovery number 19 is the strange finding of atmospheric contamination between stars. In a normal binary system, the stars are far enough apart that their outer layers, their atmospheres, remain distinct. But in the incredibly tight subgroups of a D10 system, the stars are orbiting so closely that their vast fiery atmospheres constantly brush against one another. This creates a spectacular and bizarre process called atmospheric mixing. Imagine two immense clouds of gas, each one 100 times larger than Jupiter, orbiting each other at terrifying speeds, their edges continuously overlapping and intermingling. The sheer friction and turbulence generated by this constant contact rips material from one star's surface and deposits it onto the other. Since no two stars in the system are exactly alike in mass or chemical composition, this atmospheric swapping leads to massive contamination. Astronomers use spectrometry to analyze the light coming from these stars, and they find strange, contradictory chemical fingerprints. For example, a star that should be rich in hydrogen might show traces of heavy elements like iron that clearly originated from a nearby, more metal-rich sibling. This contamination does not happen slowly. Due to the high speeds and intense gravitational drag, this mixing can occur over periods as short as a few thousand years. The stars are essentially borrowing each other's outer layers. This discovery further complicates the puzzle of low metallicity we just discussed. If a metal-poor star is constantly being contaminated by a slightly more metal-rich neighbor, the chemical signature we measure is not the star's true birth composition, but a current mixed blend. This means the stars we are observing are not chemically stable. Their surface elements are constantly changing, reflecting a continuous dynamic exchange with their immediate neighbors. While this atmospheric mixing does not directly threaten the physical orbits, it profoundly affects the evolution and measurable age of the stars, making it nearly impossible to determine their true origins. It confirms that the D10 systems are not just gravitationally connected, they are physically and chemically intertwined, blurring the boundaries between one star and the next. The constant churning of stellar atmospheres is a visceral consequence of packing 10 suns into a single, small neighborhood. The constant churning of stellar atmospheres is a visceral consequence of packing 10 suns into a single, small neighborhood. This brings us back to discovery number 19, the compelling evidence of stellar contamination through gas exchange. The incredible proximity of stars in the tight subgroups means that their vast, diffuse outer layers are not safely isolated. Instead, they are constantly overlapping and interacting. It is a slow, relentless merging of stellar skin. Every star possesses an extended outer atmosphere, the corona, which can stretch out for millions of miles. Because the orbital periods are so rapid and the stars are so tightly packed, the coronas of adjacent stars are perpetually shearing past one another. This generates immense friction and tidal turbulence, forcing a continuous two-way transfer of atmospheric gas. Astronomers analyze the light from these stars using spectroscopy, which reveals the chemical elements present in their atmospheres. What they find is baffling. Stars that should be chemically pristine suddenly display spectroscopic signatures of elements that could only have originated from their nearest neighbor. For example, a star that should be primarily hydrogen and helium might show clear evidence of nickel or iron, elements typically found only on the surface of a star with a different mass and age class in the same subgroup. This contamination is not a minor trace, it is a significant, measurable fraction of the star's surface composition. This discovery shows that the D10 systems are not just gravitationally locked, they are literally sharing their bodies. This chemical exchange has a crucial stabilizing role. By allowing the stars to bleed off excess material and exchange volatile elements, the system can subtly adjust the mass balance between the individual components. If one star became too heavy too quickly, it would throw the entire hierarchy into chaos. The continuous corrosive process of atmospheric mixing acts like a chemical equalizer, preventing any single star from becoming too gravitationally dominant and threatening the fragile stability of the remaining 9. This means that the stars in a decuple system are not only surviving chaos, they are using physical and chemical integration as a tool for survival, constantly blurring the lines of where one star ends and another begins. This makes tracking the true age and evolutionary path of any single star within the system an almost impossible task. The chaos of atmospheric mixing is merely a prelude to a far more violent event. Discovery number 20 reveals the unsettling periodicity of cataclysmic variables in decuple star systems. Cataclysmic variables are binary star systems where a white dwarf star is aggressively stripping material from a companion star. This theft of stellar fuel causes dramatic, periodic eruptions, massive stellar flares that can brighten the system hundredfold overnight. What astronomers are finding in the D10 systems is that these cataclysmic events are not random. They occur on precise, predictable schedules, almost like clockwork. This is profoundly strange. In a normal environment, the eruption of a cataclysmic variable is driven by the internal physics of the two stars and the rate at which mass accumulates on the white dwarf surface. The timing should be erratic, based on internal instabilities, yet within the crowded core of a 10-star family, the cataclysmic variables seem to be regulated by an external conductor. The massive fluctuating gravitational tides exerted by the other 8 stars act like a cosmic metronome. Every time one of the large stellar subgroups swings close to the cataclysmic binary pair, the immense gravitational drag forcibly accelerates the transfer of mass between the two stars. This creates a predictable surge of fuel onto the white dwarf, triggering the massive eruption on a scheduled cycle. It is a terrifying example of external gravity dictating internal stellar violence. The periodicity of these massive flares has 2 dramatic consequences for the system's longevity. First, the scheduled eruptions act as a pressure relief valve, violently shedding material and energy from the most unstable part of the system, preventing a slow, steady gravitational disaster. Second, the predictable timing of these massive flares introduces a new danger for any potential planets. Instead of random, lethal bursts of radiation, a planet would face a scheduled, life-extinguishing pulse of energy every few months or years. If life somehow evolved to survive these harsh conditions, it would need to develop a biological calendar based on avoiding the next scheduled cataclysm. This extreme predictability of violence suggests that even the most chaotic elements of the decuple system are being ruthlessly controlled by the overarching gravitational geometry, turning stellar destruction into a predictable, necessary function of system maintenance. The rhythmic violence in these systems suggests a gravitational puppet master is at work. Discovery number 20 details the unsettling fact that decuple star systems rarely host just one cataclysmic variable. They often contain multiple pairs of these explosive binaries nestled within their tight subgroups. A cataclysmic variable, or CV, is a binary stellar pair where a white dwarf star, the dense remnant of a sun-like star, is actively stealing material from a nearby living companion. When enough stolen hydrogen piles up on the white dwarf surface, it triggers a thermonuclear explosion, a massive sudden brightening that makes the star system briefly shine with terrifying intensity. This event is a nova, and in isolated systems, the timing of these explosions is relatively unpredictable, driven by the star's internal physics, but in the crowded gravitational pressure cooker of a D10 system, the violence is synchronized. Astronomers looking at light curves from these decuple families noticed something bizarre. When one cataclysmic variable erupted with a blinding flash, another one in a completely different subgroup would often erupt shortly thereafter, following a strange, repeating cycle. This synchronized periodicity is a phenomenon never observed in isolated CV systems. This suggests that the internal physics of the stars are being overridden by the external, overwhelming gravitational forces of the entire collective. The combined massive tidal forces of the 10 stars, including any black holes or pulsars, create a consistent, predictable gravitational ripple that sweeps through the entire system. Every time a major subgroup swings past the CV binary, that gravitational pulse forcibly accelerates the mass transfer between the two stars in the pair. This external push shortens the time required for the white dwarf to accumulate the critical mass needed for its explosive outburst. Because the orbits of the large subgroups are stable and predictable, the resulting nova events become predictable as well. The D10 system has weaponized its own chaos, turning its gravitational instability into a timed mechanism of violence. These scheduled, massive energy dumps are necessary. If the mass transfer in the CV binaries were left to its own unstable internal rhythm, it could lead to sudden, long-term gravitational imbalances that would quickly shatter the entire 10-star system. Instead, the Decuple system uses its overall gravitational geometry to enforce a scheduled rhythm of destruction, bleeding off excess material and energy through periodic flares that manage the internal pressure and keep the entire stellar family from flying apart. This is stability achieved through controlled, synchronized explosions, a terrifying way to maintain order. The synchronized violence of these star systems constantly makes them shudder. Discovery number 21 involves the incredible observation of extreme Doppler shifts and velocity spikes. Doppler shift is how astronomers track the motion of stars. As a star moves toward us, its light is compressed, shifting toward the blue end of the spectrum called blue shift. As it moves away, the light is stretched, shifting toward the red end, called redshift. By measuring these shifts, we can determine the speed and direction of the stars in their orbits. In a simple star system, these shifts are smooth and predictable, tracking a star's gentle, steady speed as it orbits. In the Decuple star systems, the measurements are anything but gentle. Astronomers routinely record sudden, massive spikes in velocity that defy the expected orbital mechanics. A star that should be moving at 200,000 miles per hour suddenly registers a speed of 700,000 miles per hour, then immediately drops back down. These velocity spikes are caused by short-lived extreme gravitational interactions within the system's core. Because the 10 stars are packed so tightly, and because they are all orbiting on those tilted, haphazard planes, the stars occasionally experience a momentary, terrifying close pass with 2 or 3 of their siblings simultaneously. This brief, powerful gravitational alignment acts like a cosmic whip, accelerating the star to incredible, almost unbelievable speeds. Think of it like a pinball machine where the star is knocked violently between 3 bumpers at once. This superacceleration is temporary, lasting only a few hours, but it violently disrupts the star's orbital momentum, injecting massive amounts of energy into the system. The sheer kinetic energy involved in these velocity spikes is staggering, and it should, by all rights, be enough to send the star flying out of the system forever. Yet the star always remains tethered. This suggests that the same gravitational geometry that creates the whip-like acceleration is also responsible for quickly absorbing that energy, slowing the star down and preventing it from achieving escape velocity. The ability of the D10 system to manage these continuous, short-lived spikes of extreme kinetic energy is a crucial mystery in its stability. It means the system is not orbiting in a slow, stately dance, but is constantly being subjected to sudden, violent, near-collision events that should kill it, but instead somehow sustain its terrifying rhythm. The light pouring from these Decuple systems tells a tale of continuous motion sickness. Discovery number 21 focuses on the constant, rapid, and extreme Doppler shifts observed in the light spectra of the orbiting stars. To an astronomer, measuring the velocity of a star in a D10 system is a computational nightmare, the ultimate test of orbital mechanics. This is because each star is constantly accelerating and decelerating under the influence of 9 other massive bodies, with no moment of steady, predictable movement. When scientists point a telescope at one of these 10 suns and analyze its light, the resulting Doppler measurements look less like the smooth sine wave of a normal orbit and more like a seismograph during a massive earthquake. The light shifts violently from blue to red and back again, registering incredible, short-lived spikes in velocity that defy standard measurement techniques. For example, a star might register a speed moving away from us at 300 kilometers per second, and then a few hours later, register a speed moving toward us at an even higher rate. These spikes are not noise or error. They are real, reflecting the moment that the star experiences a triple or quadruple gravitational alignment. the cosmic whip effect we just discussed. This effect makes interpreting the system's true velocity and trajectory almost impossible. To accurately calculate the path of one star, you must simultaneously account for the instantaneous position and gravitational influence of the other 9, which are themselves all moving at high, rapidly changing speeds. The challenge is immense. It is like trying to measure the speed of one marble in a bowl containing 9 other constantly colliding, speeding marbles, and then having to use that measurement to predict what will happen 10 seconds later. Astronomers have found that they must drastically increase the frequency of their measurements, sometimes tracking a single star every 15 minutes, just to capture the full violence of these velocity spikes. If they rely on the usual nightly observations, the extreme acceleration and deceleration would simply blur the data, making the system appear stable when it is anything but. The erratic velocity spikes reveal that the D10 systems are not just stable in spite of chaos. They are stable because they are continuously undergoing near-collision speed bursts that redistribute internal momentum, preventing the slow spiral into collapse. The extreme acceleration and deceleration in these systems means that if a gas cloud or a small object were to wander in, it will be instantly vaporized or flung out. Yet stable objects surprisingly exist. Discovery number 22 details the bizarre finding of stable Trojan star configurations within the Decuple families. In our own solar system, Trojan points are gravitational sweet spots, specific regions in a planet's orbit where asteroids can gather without being pulled toward the sun or scattered into space. These points, called Lagrange points, are extremely stable, allowing matter to settle. Now imagine finding this same phenomenon, but instead of small asteroids orbiting a planet, you find an entire full-size star occupying one of these sweet spots, trapped in the precise gravitational wake of another stellar subgroup. This is the reality of the Trojan stars found in D10 systems. Astronomers have identified instances where a tight triple star group, the primary subsystem, is being trailed by a single smaller star that is locked into a Lagrange point of the larger group's orbit. The smaller star is not orbiting the main gravitational center on its own. It is orbiting the combined mass of the triple group, following it like a fixed, obedient shadow. This level of orbital precision is breathtaking. For a star to remain perfectly locked into a gravitational sweet spot, the entire system must be flawlessly balanced. If the mass of the triple star group fluctuates even slightly, or if the orbital path is disturbed by one of the outer stars swinging too close, the Trojan star will be instantly dislodged and accelerated into a catastrophic collision. The presence of these stellar-scale Trojan configurations is the strongest evidence yet that the D10 systems are not just randomly chaotic. They possess an incredibly fine-tuned architecture where the massive objects are locked into mathematically perfect gravitational relationships. It suggests an underlying principle of stability that is far more rigorous than we previously assumed. The Trojan stars are essentially the gravitational hostages of the larger subgroup, forced into a stable relationship where they cannot move forward or fall behind, forever locked into the specific orbital rhythm of their captors. This finding confirms that the system maintains order by ruthlessly exploiting every possible gravitational loophole, even those meant for small space rocks, to anchor massive stellar components in place. The Trojan stars are essentially the gravitational hostages of the larger subgroup, forced into a stable relationship where they cannot move forward or fall behind. This precise, almost mathematical stability in a chaotic star system is perhaps the most shocking discovery made about these Decuple families. For a long time, astronomers dismissed the idea of finding stellar-scale Trojan objects. In our own solar system, Trojan asteroids are small space rocks that orbit the Sun at specific, stable points 60 degrees ahead or 60 degrees behind a major planet like Jupiter. These points, known as Lagrange points, are gravitational sweet spots where the pull of the planet and the Sun perfectly cancel out, trapping the asteroid in a fixed position. Now imagine replacing that tiny asteroid with an entire star, a full-size Sun, orbiting in the gravitational wake of 2 or 3 of its siblings. Discovery number 22 confirms that in a few exceedingly rare D10 systems, this phenomenon actually occurs. In these isolated cases, a fainter, smaller star is found locked into a Trojan orbit, perfectly synchronized with 2 massive primary stars, the smaller star is not orbiting the center of mass freely. It is trapped, held in place by the combined precise gravitational field of the 2 or 3 larger stars it shadows. This stability is absolutely astonishing because the 10-star system is already suffering from catastrophic gravitational imbalances and chaotic velocity spikes. For one star to find and maintain such a perfect, mathematically rigorous orbit while being constantly pulled and pushed by the other 7 stars in the distance borders on the miraculous. It requires that the primary core subgroup of stars be operating with an almost flawless internal balance, a level of precision that should be impossible given the ongoing star swapping and atmospheric contamination. The existence of a Trojan star is concrete proof that these Decuple systems possess islands of perfect order within their sea of chaos. These tiny pockets of stability are governed by physics so precise it suggests the system is not merely surviving, but is optimized for gravitational harmony in highly localized zones. If the mass of the primary binary component shifted by even a fraction of 1%, or if the orbital distance was off by a single mile, the entire Trojan configuration would instantly shatter, flinging the captive star into a deadly, unrecoverable trajectory. It forces us to ask whether the surviving D10 systems are simply the ones that, through cosmic chance, manage to achieve these perfect, localized gravitational setups, thereby stabilizing the entire impossible family. The astonishing stability of a Trojan star demands a perfect environment, but most of the system is pure chaos. Discovery number 23 reveals the presence of a gigantic, cold infrared dust halo surrounding the entire Decuple system. When astronomers look at these 10 sun constellations using infrared telescopes, they see something far larger than the stars themselves. The entire stellar family, often several light years across, is encased in a massive, dense cloud of cold dust and icy pebbles. This immense shroud is so cold that it barely emits any visible light, but it glows fiercely in the infrared spectrum. This dust halo presents a profound puzzle. With 10 massive suns blasting immense heat and stellar winds into the void, that halo should be instantly vaporized or blown away. Any dust that survives should glow brightly near the stars, not remain cold and diffuse at the outer edges of the system. The sheer density and cold nature of this peripheral material suggests that the dust halo is not merely debris. Instead, it seems to be actively maintained and protected by the system itself. One theory suggests that the bizarre multipolar magnetic field we discussed earlier acts as a magnetic cage, containing the electrically charged dust and preventing the stellar winds from blowing it away. The magnetic strength might be physically opposing the kinetic energy of the stellar winds, forcing the cold dust to remain trapped in the system's gravitational sphere of influence. The implications of this cold halo are staggering. It acts as an immense constant cushion for the gravitational fluctuations within the core. Every time one of those hyper-eccentric orbits pulls an outer star close to the core, the sudden energy injection is partially absorbed by this massive, dense halo, acting like a cosmic shock absorber. Furthermore, this cold, dense dust is the ultimate shield. It filters out the lethal high-energy X-rays generated by the warring stellar winds, providing a layer of protection that could be crucial for any theoretical life attempting to survive in the outermost reaches of the system. The dust halo transforms the Decuple system from a naked, chaotic monster into a carefully shielded environment, suggesting that the most complex star systems in the universe actively build their own protective shell to survive the inner gravitational violence. This massive cold envelope is a clear, visible signature of the system's fight for longevity, a dark, icy secret that holds the key to its impossible endurance. This massive cold envelope surrounding the 10 suns is actually glowing with warm, persistent infrared light. Discovery number 23 confirms that every observed Decuple star system is shrouded by a gigantic, tenuous halo of dust and gas that stretches far beyond the stars themselves. This enormous veil is the system's own self-constructed cocoon. What makes this finding so perplexing is that the sheer energy output of 10 massive suns should instantly vaporize or violently push away any surrounding dust and gas. Stellar winds from 10 stars colliding at supersonic speeds should sweep the entire system clean, leaving a vacuum in its wake. Instead, astronomers detect a diffuse, warm glow that signifies this dust is not only present, but it is trapped. The dust is too far away from the core to be heated by direct radiation, yet it is much warmer than the icy temperatures of interstellar space. This suggests the dust is held close enough to absorb some of the residual heat and high-energy friction created by the internal gravitational chaos. The survival of this dust halo points directly back to the incredible gravitational and magnetic scaffolding we have already discussed. The complex, highly organized magnetic fields generated by the interacting stellar winds likely act as an invisible net, electrically charging the dust particles and physically preventing them from being blown away by the stellar output. This immense layer of trapped dust offers crucial clues about the initial formation of the D10 systems. If the systems were violently ejected from a dense stellar nursery, they should have left all their gas and dust behind. The fact that they carry this massive shroud with them suggests that at least some of the formation process occurred in relative isolation, allowing the immense gravitational field of the 10 stars to gather and hold onto this significant residual mass. Furthermore, this dust halo acts as a thermal regulator for the entire system, absorbing the relentless X-ray bombardment from the wind-wind interaction zones and then re-radiating that energy back into space as gentle infrared light. This process is essential for the system's longevity, preventing the internal buildup of runaway heat and energy that would accelerate stellar evolution and orbital decay. The cold, massive dust shroud provides a protective shell, a necessary buffer that allows the impossible gravitational dance within the core to continue its tortured rhythm. The protective dust halo is not the only strange, quiet feature of these violent stellar families. Discovery number 24 reveals the truly unsettling phenomenon of unexplained radio silence gaps. Radio waves are the low-energy electromagnetic radiation that often pours out of star systems, generated by the energetic processes in the stellar winds and magnetic fields. Since Decuple star systems are the sites of 10 warring solar winds, continuous X-ray production, and intense magnetic chaos, astronomers predicted they should be drowning in a cacophony of radio noise. They expected a static blizzard, a persistent, overwhelming roar of low-frequency emissions. The reality is the precise opposite. When massive arrays of radio telescopes are focused on D10 systems, they often detect strange, sharp gaps of almost total radio silence within the system's core. These are narrow zones where the expected radio emissions completely drop out, falling to levels lower than those found in the quietest regions of interstellar space. Imagine trying to listen to 10 jet engines running simultaneously, only to find small, perfectly silent pockets right in the middle of all the noise. What is causing these mysterious null zones? The leading theory suggests that the complex multipolar magnetic field we discussed earlier is acting as an ultra-efficient radio filter. Instead of simply generating noise, the tangled magnetic lines are perfectly aligning in these specific zones, forcing the charged particles to follow paths that do not allow them to emit radio waves. The magnetic geometry is essentially creating a series of cosmic blind spots, absorbing or redirecting the radio energy entirely. This phenomenon is critical because it offers a rare glimpse into the perfect, localized organization within the chaos. These radio silence gaps always align with the most stable Lagrange points, or the exact gravitational center of the tightest stellar subgroups. The magnetic silence is a fingerprint of gravitational perfection, a zone where all 10 forces are in such precise alignment that they suppress the noisy byproducts of their own energetic conflict. These gaps might be the only places in the entire star system where advanced communication could be possible, where the normal din of 10 suns is momentarily muted by the complexity of their own physics. The sheer precision required for 10 magnetic fields to align and suppress all radio emission in a specific spot is astronomical, proving that the D10 systems maintain zones of impossible order. The magnetic silence is a fingerprint of gravitational perfection, holding the final clue to the impossible stability of these stellar families. Discovery number 24, the observation of unexplained radio silence gaps, is one of the most counterintuitive findings of all. Telescopes tuned to the low-frequency radio spectrum are the best tool for measuring the sheer chaos of a star system. Since the D10 systems feature 10 solar winds violently colliding and tens of millions of degrees of superheated plasma, the expected radio signature is a continuous, deafening roar, a blizzard of static that masks everything else. Yet sky surveys occasionally reveal these decuple systems flashing on and off the radio dial. They appear bright and loud, then suddenly, for periods lasting hours or days, they dim significantly in specific radio frequencies, creating baffling holes of silence in the energetic storm. These zones are not random. They always correspond to the precise gravitational center of the system or the tightest orbital subgroups. The question is, how does a gravitational nightmare of this magnitude manage to silence itself? The leading hypothesis is an elegant, terrifying solution involving magnetic cancellation. Every spinning star generates an immense, complex magnetic field. In a close orbit, these 10 massive fields are constantly fighting and twisting, but because the star systems are geometrically so precise, there are moments when the magnetic north poles of one star subgroup perfectly align with the magnetic south poles of a neighboring subgroup. This perfect momentary alignment causes the magnetic fields to precisely cancel each other out in the localized zone. The charged particles, which normally emit the radio waves as they spiral along magnetic field lines, suddenly find themselves in a temporary magnetic vacuum. Without the field lines to guide them, the particles simply stop emitting radio waves and the turbulent, chaotic core falls silent. This magnetic cancellation is rare and short-lived, demanding a perfect orbital configuration, but its very existence provides a powerful insight. It proves that the relentless, hyper-complex geometry of the decuple system is not merely chaotic. It achieves moments of profound, localized order that suppress the system's own energetic output. These radio silence gaps are the ultimate proof that the impossible dance of the 10 stars is, in fact, an exquisitely choreographed ballet, where the forces of destruction occasionally align to create brief, breathtaking periods of perfect, life-saving calm. This discovery fundamentally alters our perception of stellar stability, suggesting that the most powerful entities in the universe conceal their secrets in moments of surprising quiet. The extreme violence necessary to stabilize these star systems always carries the risk of complete catastrophe. Discovery number 25, the final unbelievable secret of the decuple star families, reveals the potential for extreme tidal disruption events. A tidal disruption event is a phenomenon where a star passes too close to a massive black hole, and the black hole's gravity stretches and tears the star apart. The star is ripped into a stream of gas, and that gas spirals into the black hole, releasing a massive flare of energy and light. This usually happens only in the core of a large galaxy where supermassive black holes lurk. But in a D10 system, we do not need a supermassive black hole to cause this kind of destruction. We only need the combined, fluctuating gravitational field of 10 massive suns and any hidden stellar remnants. The inner cores of these systems are so crowded and the orbit so complex that even a slight, unpredictable shift in momentum can send one of the stars careening toward its siblings. If a star, particularly one of the less massive partners in a binary pair, passes too close to the gravitational center of the system, the combined tidal forces of the 9 other stars act like a gigantic, invisible shredder. The star is pulled apart, not by one massive entity, but by the aggregate, overwhelming pull of the entire stellar family. This event is not a supernova. It is a slow, agonizing stellar death, where the star is physically stretched and sheared until it becomes a long stream of superheated plasma, sometimes taking thousands of years to completely dissipate. The raw energy released during one of these internally triggered tidal disruption events is immense, far surpassing the output of a standard cataclysmic variable flare. It is the ultimate pressure release valve for the system, violently removing an unstable component that threatened the overall equilibrium. The fact that the D10 systems are so precise in their orbits proves these events must be incredibly rare, but the potential is always there. The sheer concentrated mass of the decuple star system means that even without a supermassive black hole, it possesses the internal gravitational power to dismantle any star that strays too close to the core. This is the final, terrifying secret of these impossible constellations, the knowledge that their stability is maintained by the periodic total annihilation of one of their own members, confirming that survival in a 10-star family is fundamentally a ruthless, self-cannibalizing process that ultimately defies our understanding of cosmic endurance. The sheer concentrated mass of the Decuple star system means that even without a supermassive black hole, it possesses the internal gravitational power to dismantle any star that strays too close to the core. This is the final terrifying secret of these impossible constellations, the knowledge that their stability is maintained by the periodic total annihilation of one of their own members, confirming that survival in a 10-star family is fundamentally a ruthless, self-cannibalizing process that ultimately defies our understanding of cosmic endurance. Discovery number 25 is the true potential for self-destruction within these complex structures. The systems we observe today are only temporarily stable, and within them lurks the terrifying future certainty of extreme tidal disruption events. As these 10 massive stars age, they do not simply fade quietly, they expand. When a star like our own sun nears the end of its life, it puffs up dramatically into a massive red giant, swelling to hundreds of times its original diameter. Now imagine 10 of these massive stars, already orbiting so closely that their atmospheres are brushing, suddenly swelling to fill even more of that limited space. This stellar expansion is the ultimate death sentence for the system's longevity. The increase in size drastically magnifies the probability of a physical collision, or more likely, a catastrophic close pass. When a swollen, dying star comes too close to the concentrated center of mass, the immense fluctuating gravity of the 9 other stars, plus any hidden black holes or pulsars, acts like a stellar meat grinder. The tidal forces generated by this close pass would stretch that star into an impossibly long, thin streamer of superheated gas, tearing it apart atom by atom. This is an internally generated tidal disruption event. Scientists predict that these events will not be one-off accidents, but rather the inevitable, final fate of many of the Decuple star systems. The very chaos that sustains them now guarantees their future demise. Observing such an event would be a monumental moment for science because it would allow us to study extreme gravity in action, watching as the universe's most complex gravitational architecture violently shreds one of its own. It would provide irrefutable data on how gravity behaves when 10 massive bodies are involved in the final, catastrophic act of stellar cannibalism. The Decuple star systems are not eternal. There are ticking gravitational time bombs, and the extreme violence necessary for their formation will ultimately be the cause of their explosive destruction. The 10-star families are destined for destruction, but their brief existence teaches us a profound lesson about the universe. What do these impossible constellations ultimately reveal about the nature of order and chaos? The 25 strange discoveries we have uncovered are not just isolated facts about bizarre star systems. They are glimpses into a level of gravitational and energetic complexity that fundamentally redefines the limits of cosmic stability. We learn that order is not achieved through isolation and simplicity, but through the ruthless management of extreme chaos. The Decuple systems survive because they have perfected methods of self-cannibalism, magnetic shielding, and synchronized violence, turning the very forces that should destroy them into mechanisms for survival. This suggests that the early universe might have been far more capable of producing highly complex, unstable, but enduring structures than we ever believed. We often look at our own calm, predictable solar system as the cosmic norm, the ideal standard for planetary survival and stellar longevity. The D10 systems shatter that perspective. They show us that order is merely a localized state, a brief fragile pocket of calm carved out of a massive sea of gravitational and energetic warfare. These 10-star families are living proof that maximum physical complexity and massive power can sustain themselves for billions of years, but only by constantly sacrificing their own members and relentlessly fighting the natural forces of collapse. They stand as a warning that the universe does not always favor the slow, gentle, predictable path. Sometimes the only way to endure is through violence, adaptation, and an almost miraculous level of gravitational perfection. The mystery of the Decuple stars is a mystery of endurance, forcing us to rethink every model we have about how complex systems are born and how they die, and whether true stability even exists. The Decuple star systems are nature's ultimate gravitational laboratories. We have journeyed through 25 strange, complex, and boundary-pushing discoveries that have fundamentally redefined what is possible in the night sky. Witnessing the impossible architecture of formation, the constant star swapping, and the hyper-eccentric orbits forces us to throw out our dusty old textbooks on stellar mechanics. These systems are not gentle, predictable clocks. They are massive, powerful machines that survive only by enforcing zones of synchronized violence, magnetic suppression, and gravitational perfect order. They demand we accept that stability in the universe is often achieved through the ruthless management of chaos, from the deep perplexity of the missing mass conundrum, likely solved by hidden black holes and pulsars, to the strange stillness of the radio silence gaps. These 10 sun families reveal a universe far more ingenious and violent than previously imagined. They build their own protective dust halos, enforce life-extinguishing scheduled cataclysmic flares, and maintain impossible orbital perfection through the existence of gravitational hostages like Trojan stars. Reflecting on this chaos, a very personal question arises that we must all confront. If such extreme volatility can endure for billions of years, how truly stable is our own quiet, 8-planet solar system? Are we simply in a temporary pocket of calm, awaiting our turn for a gravitational rearrangement that could shatter our predictable orbits? Perhaps the most important secret the D10 systems hold is not about them, but about the fragile, temporary nature of stability everywhere. Which of these 25 mind-bending discoveries about the Decuple star system shocked you the most? Was it the star-eating vampire pairs, the synchronized nova, or the terrifying gravitational distortion that proves nothing is safe from the sheer power of 10 competing suns? We want to hear your thoughts in the comments below. Join the conversation and tell us which discovery you found the most unsettling reminder of the universe's chaotic power. And if you want to keep exploring the edges of cosmic mystery, make sure you hit that subscribe button for more deep dives into the unbelievable secrets hidden in the cold, dark void.